Happy Sunday, my friends. So in this video, I'm going to show you how to implement the n-step binomial tree model in Python for both European and American options for both calls and puts. I'm going to try to make this video as standalone as possible, but it's actually part 5 of my series on the binomial tree option pricing method. The previous videos didn't get so many impressions, like barely any views, barely any impressions. So for this video, I'll ask if you do enjoy the video, please like and subscribe and share. Thank you. That would help a lot because I don't know if anyone cares because I got like no views. But anyways, let's get to business. In the next video, I'll actually show you when you take n, the number of time steps, to get very large, it will converge to the Black-Scholes formula. So let's get started. So the first thing is, let me get rid of my picture because it'll block things later on. Okay, so I got rid of my picture, so now we can start. Okay, so what is the so the idea of this video is we basically want to create a calculator, and the calculator is basically going to take usual inputs for options like the strike price, the initial stock price, the volatility, the risk-free rate, and the time to expiry. So, by the way, for all these option pricing things like Black-Scholes, binomial tree, the convention is usually to state volatility, the risk-free rate, like annually or in years. Like, so time to expiry would be in years, and risk-free rate and volatility is going to be annual. And because t is our time to expiry, the number of binomial steps, if we set that to n, that means our step size, like in the previous videos, is going to be h equals t over n. Okay, so and strike price is k, initial stock price is S0, volatility is sigma, and so on. That's our notation. Okay, so let's get started. First, let me introduce some important notation. By the way, the idea is still going to be like in the previous video. To price these options is we're going to go backwards in time since we know the payoff at expiration, and we'll go backwards in time until we get to initial time at the initial stock price. So let me just explain how it is. So let's just introduce some notation. So if we let Vt of S denote the value of the option at time t for stock price St equals S. So this means t starts at time 0 and it goes to time capital T, the expiration. And this means if you're at time t anytime and the stock price is S, what's the value of the option there? So let's just introduce some notation that you'll see why it's helpful in a second. So we'll let V underscore ij be if you're at time j times h, meaning you're at time step j, but because each time step is of size, time intervals of size h, so you'll be at time jh, and the stock price is going to be S underscore 0, the initial stock price, u to the I, d to the j minus I. So basically, whatever your time step you're at is going to be the j here and dj minus I. So if you're at time step 10, it'll be d to the 10 minus I, and u to the I times d to the 10 minus I, and so on. So let me explain. It'll make a little bit more sense in a second when I show you guys, like, as in the previous video, we have like the dynamics of the stock price. So we're not going to show it as like a tree here. We're going to show it actually as like a table. And it'll make sense because this is how we're going to actually implement it in Python. So the way to think about this is think about the j's as the index for the time step. So time step 0 means the initial time. This is time step 1 all the way up to time step n because we have n steps, right? So n of these 0 to 1, 1 to 2 intervals, right? So j is the time step. And for each j, you have these i's. I's are the different possibilities for the stock price. So if you're at time 0, the stock, the only option at time 0 is the stock price to be 0. But at time 1, the stock price can either go up to S0u or down to S0d. So there's two possibilities. At time 3, it can go up to S0u squared, down to S0ud, but then if it went down the first time, it can go from S0d to S0ud, and then to S0d squared. So time 2 would have 3 options. And in general, time step j equals 4 will have 5 different options. It'll have j plus 1 different stock price options, right? And remember, the convention from the previous videos is that U equals 1 over D. So the tree is connecting, meaning if you go up and then down, it's the same as going down and then up. But the convention here is if you go down, you stay at the same level I. So if you're basically, let's just show this example, you're at time 3, step 3, and the stock price is S0 U squared D. If the stock goes down, it goes to S0 U squared D squared, but it stays at the same I level. But if it goes up, it goes to S0 U cubed D. So that's our convention, and you'll see why we do that for the programming. But in general, what happens is, like, let's say you're at time step 4, you have D to the 4 minus I. I is 0 here, so that's why you don't see it. So the D goes from 4 to 3 to 2 to 1 to 0, and the U goes from U to the 0, U to the 1, U to the 2, U to the 3, and so on. So that's the way the price dynamics works. And when you get all the way to time n, you see you go from U to the 0 times D to the n, D to the n minus 1 times U to the 1, D to the n minus 2 times U to the 2, all the way to D to the 0 times U to the n minus 0. So that's the expiration at time t equals n, and intervals of size h equals big T. Okay, so hopefully that dynamics makes sense. And also for the option price itself, remember our notation is like this is the option price at time step 3 for this stock price S0 U cubed. So that's also time step 3 is also time 3h. And basically, if the stock goes up, the option price is this. If the stock goes down, the option price is this. So that's the way to look at it. Okay, so the idea is, this will be more clear when I write the code. So idea is, like in the previous video, 2 videos, is we're going to go backwards in time from the expiration, because we know the payoff, all the way up to time 0, and that's how we're going to get the option value. So just a few small little bookkeeping type things. So number 1 is the payoff function, of course. If it's a call option, it's going to be the stock price minus the strike price, or 0. The max of that or 0. If it's a put, it's going to be the strike minus the stock price or 0. So K minus S or 0. And that's our payoff function. I guess I shouldn't have called it P, but couldn't think of a better thing. So remember, the way we price these options, if it was European option, is we had this like risk neutral probability where we had like the value of the option at this node is the probability, the risk neutral probability, times the payoff if the stock went up, times 1 minus the risk neutral probability, times the payoff if the stock went down, and you discount it by e to the negative RH, by a discount factor. So this P star, remember, this is a risk neutral probability, but it's the one used to price the options to have 0 arbitrage. It's not the real world probability. The only requirement of the real world probability, of course, is that it's strictly between 0 and 1. Of course, we're making some assumptions like volatility is constant. It's obviously not in real life. The risk-free rate is constant. Obviously not in real life. Things like that. No transaction cost. All this other stuff. But like for this model, it's reasonable. So the risk neutral probability is, as in the previous video, you can use this formula, e to the RH minus D over U minus D. Okay, so and another quick thing is we never specified what U and D should be. If I get enough questions asking how to derive this, I'll show you guys how to do that. But it's with something called like volatility matching. And the most common thing is the Cox Ross Rubenstein model, so CRR model. And they choose U as e to the square root of the time interval times sigma. And D is just 1 over U, so it's e to the negative square root of the time interval times sigma. So they do it with something called volatility matching, but that's out of the scope of this video. Okay, so now basically the algorithm we're going to implement with Python is some backward induction. So at expiration, we know the value of the option. It's the payoff that we defined earlier, whether it's a call or put option, of the stock price, which will be, if it's VIN, remember by the formula, it'll be U to the I, D to the N minus I times the initial stock price, or K, and K. That's the payoff function. So if it's a call, it'll be this minus this, max of that or 0. If it's a put, it'll be this minus this, max of that or 0. So those are the value at, so you calculate all the values at the last time step, right? And then you go backwards in time. Okay. So first, let's talk about the European case. So like you're at time step J and node I. So if you go up in the next time step, you'll go, as we said, by our convention, you're going to go to I plus 1, and the next time step is J plus 1. And if you go down, you're going to stay at the same I level. So you're going to go VI J plus 1, because you're going to stay at the same I, but you're at the next time step. And then you multiply this by the risk neutral probability, P, oh, sorry about that, P star. I guess the internet's going crazy. And then this is 1 minus P star. When the internet goes crazy, it doesn't render. Okay, so this is like the discounted expectation of the risk neutral probability. So basically just use this formula, in other words. That's how you get the value of the previous node. But if it's an American option, you're allowed to exercise early, so you have to check the payoff here. And if the payoff at this node is actually larger, this should say J minus I, sorry about that. So it'd be S0 times UI times D of J minus I, or the discounted expectation under the risk neutral probability, as we said here. So the max of that, this should be an I. So you keep going backwards in time until you get the option price at time 0, which is going to be the thing we're looking for, which will be V00 with our notation. Anyways, I rambled a bit too fast. Let me show you guys how to do it in Python. I hope I'm not cutting off some of the screen. Okay. Okay, so let's show you how to do it in Python. Okay. So let's first, the only library we're going to need is NumPy, so import NumPy as NP. Okay, so what do we want to do? So we want to, let's write our inputs first. Just remember what we need. We need the initial stock price S. Let's just say it's 100. We need a strike price 105 or something like that. Sigma, let's just make it, I don't know, 0.2. R, let's make it 0.05, reasonable values for today. And let's make time to maturity be a year. Let's make number of time steps N equals, let's say 100 for this example. In the next video, I'll show you when you make N very large, it'll be the same as Black-Scholes. And let's also have a parameter called kind. And this can be either call or put, but we'll make it like call. And then let's also make a thing called let's make a thing called style, and it can be like American or European. Let's just make it European. For call options with no dividends, without transaction cost and taxes, it's the same price in theory, but with in practice, not always. And anyways, okay, so these are the parameters. So now we need to define a model called def binomial tree price. And so what's the binomial tree price? So we have as input S, we have K, we have sigma, we have R, we have T, we have N, we have kind, and we have style. So first, let's do a few asserts. Let's do assert kind in call put. Must be call or put. Assert style in European American. Must be European or American, something like that. Okay. So let's do kind equals call, style equals let's do European by default. Okay, so let's just see that the asserts worked just for the hell of it. So if I do this and I make it like this, do I get an error? Assertion error, must be European or American. So if I spell American, it should be good. Call, if I do this, it's wrong. I get assertion error. Okay, so that's good. The assert is reasonable. Okay, so now let's, okay, so we know the payoff function. Let's define the payoff function. So def payoff, and so we can make it sk, and then we can do kind. So again, let's just, we're gonna double assert. We don't need this twice, but I don't know. We'll put it here anyway. So if kind equals call, then what's the payoff gonna be? It's gonna be max s minus k 0. Else, because of that assert, that's okay. It's gonna be for a put. It's gonna be max k minus s 0. So that's the payoff. So I'll return that. Okay, so this is the payoff. Maybe I'll call it actually intrinsic value. Intrinsic value. Okay, so now let's go backwards in time. Okay, so we have n time steps. So we're gonna do 4 t. Let's just do the let's do the terminal time steps separately. At expiry, basically we used j for the horizontal things, so we do j equals n. We know the option values, so it's going to be basically for I in range. Remember, remember we said there's j plus 1 option, so n plus 1 in this case. It'll be 0 to n. So the stock price can be s times u to the I times d to the n minus I, like this. That's the stock price, and we need intrinsic. We need to call intrinsic value of the stock price, and the strike k. So this should probably work. And then I had a kind thing here. Call or put. Okay, so great. So this should give us our intrinsic value. Oh, and we need this thing. I'm not gonna be efficient with memory, so let's just make it np dot zeros of shape. Let's do n by n. Is that what we need, or we need n plus 1 by n plus 1? That's probably more likely. Okay, so we have v of n. V of I n, because this is going to be the time step, the second thing, because I'm using convention that vertical is the first thing and horizontal is the second thing. Although early in school we learned x is the horizontal and then y is the vertical, but later in matrices that's like the convention, so let's keep it like that. And now we're going to go backwards in time, so we'll go backwards in time. Okay, so we're going to basically have two conditions. We're going to either have, first of all, there's a few things we needed to calculate that we didn't. We needed to calculate u and d. So u equals and d equals. So d equals 1 over u, that's easy. But u equals np dot x sigma times np dot square root of h, and then d is 1 over u, and then p star, which is a risk neutral probability, I call it p risk neutral, equals what was the formula? It was e to the np dot x r times h minus d over u minus d, something like that. Okay, so now we're going to go backwards in time. So we're going to do 4, and j is the index in time. For j in range, n plus n, we're going to go n, and sorry, n minus 1 is our first thing, because we already did n. We're going to go down minus 1, so we're going to go backwards, and then we're going to do 4i in range j plus 1, because remember we had time step j, we have j plus 1 different stock values. So the stock price, of course, is going to be this quantity, but we only need that if it's American. So okay, so let's have two cases. Okay, so we're gonna have okay, so let's call this let's have two things. We'll have early exercise value. So we'll have something like if it's a style equals American, we're gonna have this early exercise value thingy. Okay, so no matter what, we're gonna have this discounted expectation. We're gonna have this discount factor, remember, equals np.x. Let's actually put the discount factor here. Discount factor equals np.exp negative r times h. So that's a discount factor. So our value is going to be actually Vij equals p risk neutral times first of all, discount factor times p risk neutral times if the stock goes up, you're at I plus 1, j plus 1. If the stock goes down, you're at 1 minus p risk neutral times, remember, if it goes down, it stays at the same height, so it's going to be I, and then j plus 1, next time step. So that's our, let's call this, let's call this continuation value. Continuation value. So this is the value of the European option, right? It's a continuation value. But like, if it's an American option, you also have this early exercise value, which is going to be basically, and I probably made a mistake because I'm going so fast. It's going to probably be intrinsic value of the value of the stock is going to be S times U to the I times D to the J minus I. So that's that, and K, great. So that's the early exercise value. So if the style is American, then we're gonna have Vij equals max of early exercise value and continuation value. And otherwise, we're just going to have Vij is just going to be the continuation value. We don't have to worry about early exercise for European. Okay, so this might work, and then we're going to return V00. Since I did it so fast, I probably made a mistake, but let's see if this works. So let's do a binomial tree price. I know about what I should get. So if I do this, oh, I need to define H. So H is going to be T over N. What else? Shape equals, okay? That is obviously wrong because the value of the option is not 0. So what did we mess up? We went backwards in time. N minus 1 is here. Oh, I know the problem. The J is going N minus 1 all the way to 1, but we need it to 0. And to 1 actually means till 2, so we need to minus 1. So then it stops at 0. So now we get a reasonable value. 8.02 is this. And because it's a call option, for non-dividend paying and no like crazy short sale fee and stuff like that, and taxes, and you're gonna see that it should be the same value. For put options, it could be different. Let's check. So we'll make it a put for a second, American put, and now let's do. Ooh, that looks a bit weird. Actually, it makes sense. And now we're gonna do European. Let's see if this makes sense. And you see the European put is less than the American put. Early exercise, the maxes in the middle make this value bigger. So hope you enjoyed it. In the next video, I'll show you if you set N very, very large, you'll get the same thing as Black-Scholes. Thank you guys. Let me put my picture back maybe if I can get it. Oops, sorry. my picture is lost forever. There we go. Too big now. Too big to be true. Anyways, if you guys enjoyed this video, please like and subscribe. Thank you guys so much and have a great day.